Most people encounter computers only through their surfaces. Screens, keyboards, sounds, sensor machines reacting to commands. This is where attention naturally goes. But Feynman's way of thinking about computers moved in a completely different direction. He believed that focusing on what goes into a computer and what comes out of it creates a false sense of understanding. Inputs and outputs may look impressive, complex, or even magical, but they distract us from the only part that truly matters. If you actually want to understand what a computer is, Feynman insisted, you have to ignore appearances and look squarely at what happens in the middle. That shift alone changes everything. Instead of asking what computers can do, Feynman asked a far more basic and uncomfortable question. What are computers? Really? His answer was that computers appear mysterious only because people confuse the outer shell with the internal mechanism. Whether information enters through a keyboard, a microphone, sensors in a car, or signals from a machine makes absolutely no difference. Likewise, whether the output appears as a picture on a screen, a sound, or the control of an engine does not change the nature of computation at all. Strip all that away and the core remains the same. Feynman drew a sharp line between the peripheral parts of a computer and what he called the computer proper. The peripherals exist for interaction. They translate real-world signals into electrical form and translate electrical signals back into forms humans can see, hear, or act upon. But none of that explains computation. The real computer exists entirely in the middle, where electrical signals are processed according to rigid, precise rules. If you don't understand that middle, you don't understand the computer, no matter how fluent you are with screens and keyboards. To make this unavoidable, Feynman deliberately abandoned modern imagery and replaced it with something ordinary and familiar, a filing system. This wasn't a casual metaphor. It was a literal description of what computers fundamentally do. According to Feynman, computers are not primarily calculating machines, despite their name. Arithmetic is just one small activity they can perform. Their real function is handling information, storing it, retrieving it, modifying it, and placing it back in an organized structure. That's why people inside the computer industry often prefer the term data handler. It's less glamorous, but far more accurate. Once you adopt this perspective, the mystery dissolves. Filing systems existed long before electronics. Offices were filled with cabinets, drawers, and cards, each holding bits of information. A computer is simply an extremely fast, highly organized, automated version of that same idea. Everything else, the lights, the screens, is decoration. Feynman began by asking us to imagine a traditional business filing system. Rows of drawers filled with cards. Each card represents a salesperson. On the card are written facts: name, address, commission rate, monthly sales. The system itself is completely passive. It contains no intelligence. Intelligence appears only when a human file clerk interacts with it. Suppose a manager asks how much commission a particular salesperson should be paid. The clerk retrieves the card, reads the numbers, performs a calculation, and writes the result somewhere, maybe on the same card, maybe on another. What matters here is not the business context, but the structure of the activity. Feynman broke it down ruthlessly, taking a card from a location, reading information from it, doing something to that information, writing new information onto a card, and returning cards to their places. From Feynman's point of view, These steps define the essence of information processing. It doesn't matter whether the task is calculating commissions, adding totals, or filtering cards based on location. The same basic operations repeat again and again. Once you see that, human intuition becomes unnecessary. Everything reduces to procedure, even arithmetic. Something people often treat as deeply intellectual collapses into mechanical steps. The clerk doesn't need to understand what the numbers mean. He copies values onto scrap paper, applies a rule, records the result. The intelligence is not in the filing system. It's not even in the cards. It exists only in the rules being followed. Feynman then pushed this idea in a direction that makes many people uncomfortable. What if the file clerk isn't intelligent at all? Suppose you hire someone much faster, quick hands, quick movement, but incapable of doing arithmetic mentally. At first glance, that sounds useless. But Feynman showed it isn't. Arithmetic knowledge can be replaced with lookup tables. Multiplication becomes nothing more than finding the right card in a multiplication file and copying down the answer. This is one of Feynman's most important insights. Procedures can replace understanding. Tasks that look like they require intelligence can be performed by systems that blindly follow instructions, provided those instructions are precise and supported by stored information. The faster clerk may require more steps, but each step is simpler, and because he's fast, the overall process can still win. Feynman exaggerated this on purpose. Each new clerk is faster but knows less. One can't multiply. Another can't add. Eventually, the clerk can't even recognize numbers or letters. He can only distinguish between two alternatives, one mark or another, one color or another, one signal or no signal. And here's the crucial point: even this extremely limited clerk can still do meaningful work if the system is organized correctly. All instructions can be written down in advance. The clerk doesn't need memory. He doesn't need judgment. A simple counter tells him which instruction comes next. He reads it, performs it, increments the counter, and repeats. Thinking disappears entirely. This is not metaphorical. This is how real computers work. A computer doesn't understand instructions. It doesn't know why it is doing anything. It simply executes steps in sequence. What people call logic, or reasoning, is nothing more than stored instructions combined with a mechanism for stepping through them reliably. Limiting the system to only two distinguishable states, yes or no, on or off, 1 or 0, is not a weakness. It's the foundation of reliability. With only two states, systems become easier to build, easier to check, and easier to scale. Enormous amounts of information can be uniquely represented using surprisingly small numbers of binary distinctions. This is why computers don't need to resemble human thought. They don't reason or interpret. They classify, retrieve, and transform information mechanically. The appearance of intelligence comes from speed, precision, and scale, not from understanding. At this stage, Feynman's conclusion becomes unavoidable. A computer is not a thinking machine. It is an automated filing system operating at electronic speed. Its power comes from relentless execution, not insight. And this understanding completely changes expectations. It clarifies what computers excel at and what they will never do naturally. It also prepares us for the next question Feynman tackled. If computers are this simple internally, how do they handle such overwhelming complexity? That's where the story goes next. Once Feynman strips away the illusion of intelligence, the next step becomes unavoidable. If a computer is nothing more than a mechanical filing system, then its real power must lie entirely in instructions. Not intelligence. Not creativity. Instructions. And this is where most people get uncomfortable, because it forces us to admit that many activities we associate with thinking can be reduced to procedures. Feynman's thinking here is sharp and deliberately provocative. He shows that when people say a computer decides, what they really mean is that the computer follows a branching instruction. If a condition is met, it goes one way. If it is not met, it goes another. That's a no judgment, no interpretation, just conditional execution. Go back to the clerk. The clerk has a list of instructions written on paper. Each instruction is simple: pick up a card, compare two symbols, copy one symbol, move to another drawer. After each instruction, the clerk advances to the next one. There is no memory of the overall task, no understanding of why the task exists. The clerk doesn't even know he is calculating commissions or sorting customers. He is executing steps. This is exactly how a computer operates internally. Every complex program, no matter how sophisticated it appears on the outside, reduces to a long sequence of extremely small, extremely boring operations. Move data from here to there. Compare two values. Jump to another instruction if a condition is met. Feynman emphasized that this is not a limitation. It's the reason computers work at all. The simplicity of the operations is what allows reliability. When machines attempt to mimic human-style understanding, they fail. When they stick to rigid procedures, they succeed spectacularly. At this point, Feynman introduces one of the most important distinctions in computing data versus instructions. Both are stored in the same way. Both are treated as information. The computer itself does not know which bits represent instructions and which represent data. That distinction exists only in how the system is organized. This idea was radical when first introduced. People instinctively assume that instructions must be special, that they live somewhere different from data. Feynman shows that this intuition is wrong. Instructions are just another kind of information. They are stored, retrieved, copied, and modified exactly like everything else. This single insight unlocks enormous power. If instructions are data, then programs can manipulate programs. Systems can modify their own behavior. Software can generate new software. What looks like learning or adaptation emerges not from intelligence, but from recursive application of procedures. Feynman was careful here. He did not claim computers understand what they are doing. He claimed something far more unsettling: understanding is not required for performance. The appearance of understanding can arise entirely from structure. Consider arithmetic again. When a computer adds two numbers, it does not know what numbers are. It follows a sequence of bit-level operations, checking carries, flipping states, advancing positions. Humans see meaning. The machine sees patterns. Feynman pushed this idea further by emphasizing the role of representation. How information is represented determines what operations are easy or hard. Roman numerals make addition painful. Binary makes it trivial. The machine does not care about elegance or intuition. It cares only about consistency. This is why computers are built on binary logic. Two states are enough. Anything more introduces ambiguity and error. With binary, signals can be refreshed, amplified, corrected. Noise can be tolerated. Precision can be enforced. At this stage, people often object, but real computers feel far more complex than filing systems. Feynman's response is simple and devastating. Complexity does not arise from complicated operations. It arises from sheer quantity. Millions of simple operations, executed relentlessly, produce effects that appear intelligent. The filing clerk example scales. Add more drawers. Add more cards. Add more instructions. Speed up execution. Nothing fundamentally changes, but the results become astonishing. This explains why computers excel at tasks humans find tedious. Sorting, searching, checking consistency, these are not intelligent acts. They are procedural acts. Computers do not get bored. They do not forget steps. They do not drift. Feynman also dismantles another common misconception here, that computers are fundamentally mathematical devices. Mathematics is incidental. Computers manipulate symbols. Mathematics happens to be a domain where symbol manipulation produces powerful results, so we associate the two. But computers are just as happy processing text, images, sounds, or any other encoded information. This reframing is crucial. Once you stop thinking of computers as calculators and start thinking of them as symbol processors, their universality becomes obvious. Anything that can be described symbolically can, in principle, be processed by a computer. And that leads directly to the next idea Feynman tackled. Perhaps the most important of all, if computers blindly follow instructions, where do errors come from, and why are they so dangerous? That question takes us deeper into the architecture of computation itself. Once you truly accept Feynman's idea that a computer does not understand anything it does, a new and uncomfortable question appears immediately. If computers are just blindly following instructions, then why do we trust them so deeply? Why do we let them handle finance, medicine, aviation, communication, even decisions that affect human lives? Feynman's thinking here becomes very practical, almost philosophical, because he is not interested in praising computers. He is interested in understanding their limits. And for him, the danger of computers does not come from intelligence. It comes from misplaced trust. A computer will do exactly what it is instructed to do. Not what you meant. Not what you meant. Not what seems reasonable in context. Exactly what the instructions specify. No more, no less. This is not a flaw in the machine. It is a flaw in how humans think about machines. When people talk about computer error, Feynman points out that this phrase is usually dishonest. The computer did not make a mistake. The instructions were wrong, incomplete, or based on false assumptions. The machine simply executed them faithfully. This distinction matters because it shifts responsibility back to where it belongs. Humans write programs. Humans design systems. Humans choose what problems to automate. When something goes wrong, blaming the machine is a way of avoiding accountability. Feynman emphasized that computers are extremely literal. They cannot interpret vague language. They cannot fill in gaps. They cannot apply common sense. Every condition must be specified. Every case must be handled. Every exception must be anticipated. And if it isn't, the machine will still act, just not in the way you expected. This is why control is the central problem of computing, not speed, not power, control. As systems grow more complex, it becomes harder to understand what they are actually doing. Not because the computer is hiding anything, but because humans cannot easily reason about millions of interacting instructions. The very thing that gives computers their power, massive scale, also makes them dangerous when poorly designed. Feynman was deeply skeptical of claims that computers could replace human judgment. not because he underestimated machines, but because he understood them too well. Judgment requires context. Context requires meaning. Meaning is not something computers possess. A computer can optimize. It can search. It can simulate. But it cannot decide what ought to matter. That decision is always external, always human. This is where Feynman draws a line that many people still ignore today. He distinguishes between process and purpose. Computers are unmatched at process. Humans are responsible for purpose. When those roles get confused, systems become dangerous. He gave examples where automated systems produced results that were technically correct but practically absurd. The machine followed the rules perfectly. The rules were the problem. Another crucial idea here is verification. Because computers are deterministic, in principle, their behavior can be checked. But in practice, verification becomes incredibly difficult as systems grow. You cannot simply test everything. There are too many possible states. This leads to a false sense of security. A system works in testing, so we assume it will work in reality. Feynman warned against this assumption. Reality always finds edge cases. And computers, unlike humans, cannot recognize when they are in unfamiliar territory. Humans notice when something feels wrong. Machines do not. They continue. This is why redundancy, simplicity, and transparency mattered so much to Feynman. He preferred systems that could be understood over systems that merely performed well. A fast system you do not understand is a liability. He also addressed the myth that more complex systems are inherently better. Complexity often hides errors. Simple systems expose them. Computers tempt us to build complexity because they can handle it. That does not mean we should. At this point, Feynman connects computing back to science itself. Science progresses by understanding, not by authority. Computers can generate answers, but they cannot explain them. If a system produces a result that no one understands, it has not advanced knowledge, it has obscured it. This is especially dangerous when people treat computer output as unquestionable. Numbers feel objective. Screens feel authoritative, but the authority is borrowed. It comes from human trust, not machine insight. Feynman's warning here is subtle but profound. The more powerful our tools become, the more disciplined we must be in how we use them. Computers amplify both intelligence and ignorance. They do not discriminate. And this brings us back to the central theme that runs quietly through all of Feynman's thinking about computers: humility. Not awe, not fear. Humility. Computers are not mysterious. They are not magical. They are not thinking entities. They are extraordinarily fast, extraordinarily obedient symbol manipulators. When we treat them as anything else, we misunderstand both them and ourselves. Understanding computers, in Feynman's view, is not about learning machines. It is about learning how human logic behaves when scaled beyond intuition. The machine is the mirror, and once you see that clearly, the conversation shifts. The question is no longer what computers can do. The real question becomes what humans should ask them to do, and what we should never delegate at all. That question does not belong to engineering alone. It belongs to judgment, ethics, and responsibility. And this is exactly where Feynman takes the discussion next.